Okay, so in the last video we went through the mole ratio from one substance to one substance, just going from A to B. But now what we're going to talk about is what happens when you have a limiting reactant problem. So what will happen here is you're going to have quantities of two reactants. And what will happen with that is you're going to have to figure out which one runs out first. Like the example we looked at on the first video, we had a mass of octane and then nothing about the other reactant, oxygen. So we just assume it's excess. If there's no quantity indicated, we just assume it's present in excess. But what will happen here is we're going to have a problem where we're going to have a mass or a quantity of two of the reactants. So this example here, it says we've got 10.2 grams of HCl is added to 13.2 grams of iron 2 sulfide. And we want to know how many grams of H2S would we form. So we have the H2S is our B, it's where we're headed. Whatever your question mark is always where you're going. And we have a starting quantity of the iron 2 sulfide and a starting quantity of the HCl. And looking at those two numbers, you can't tell which one's going to run out first. So limiting reactant problems, the way that I've always treated these is I take my first A1 and go to B. Then I start over, take my A2 and go to B, and then circle the smaller, right? Whichever one produces the smaller amount of product is the limiting reactant and runs out first. And whatever runs out first obviously says how far the reaction can go. So it looks like very similar flow chart to what we had on the first video. We've got a mass of reactant, so we'll need molar mass to get to moles. We're looking for mass of product, so we'll need the molar mass to get to moles. So starting with my A1, my iron 2 sulfide, I've got 13.2 grams of FeS. So molar mass from the periodic table, iron 55.85, sulfur 32.07. I have 87.92 grams per mole of FeS. Your center point is always your mole to mole ratio. So balanced equation for every 1 mole of FeS, make sure you go to your product. We make 1 mole of H2S, and then to get to grams, for 1 mole of H2S, 32.07 added to 2 hydrogens, I get 34.09 grams for the molar mass of the H2S. So taking my 13.2 divided by 87.92 and then times 34.09, I get 5.12 grams of H2S. Now that calculation assumes that I have plenty of hydrogen from the HCl to make that H2S, and I don't have plenty, I have a specific amount. So now I start over with my 10.2 grams of HCl, going to moles first, molar mass 36.46 from the periodic table. Always the center point, the mole to mole ratio, in this case for every 2 moles of HCl, I make 1 mole of H2S. And then that molar mass is the same, 34.09 grams per mole of H2S. So if I take 10.2 divided by 36.46 divided by 2 times 34.09, this one says 4.77 grams of H2S. So at this point, what I understand is my iron 2 sulfide could make 5.12 grams of hydrosulfuric acid. The 10.2 grams of HCl could only make 4.77. So the most I can make is the 4.77. And so my max, what's called theoretical yield, all right, of the H2S is 4.77 grams, and that is because the 10.2 grams of HCl was the limiting reactant. It ran out first. Because once that 4.77 grams of product was made, all of the HCl is gone. All right, so theoretical yield, right? Because in theory, if everything is perfect, this is what should happen. We're using perfect molar mass values and molar coefficients, so if everything's good, that's what we should get. Now, we're going to look at an actual yield in here in just a little bit, but the calculations, your stoichiometric calculations always give you theoretical yield, right? In theory, if everything's perfect, that's what we should get. The next example, we've got acetic acid with ipentanol. And it says we want to know the percent yield if 19.2 grams of ipentyl acetate was made from reacting 25.0 grams of the ipentanol with 25.0 grams of acetic acid. All right. So what's different about this question is you can see you're given quantities of two reactants and the quantity of a product, and we're being asked for the percent yield. Okay, so percent yield is when you take what's called the actual yield over the theoretical and then times 100. Now, if you're doing a percent yield, right, it's a yield, so it's always going to be looking at the product. So the reason why I point that out is when you look at the quantities that are given to you in the question, only one of them is about a product, the 19.2 grams of the ipentyl acetate. And the actual yield comes from actually doing the experiment. And since we're not in lab, that has to be given to us. So whatever mass of product that's given to you, that's going to be the actual yield, right? That was the actual mass of ipentyl acetate that was made in this reaction. So what is kind of good about pulling that out is to understand this is not a starting point. That's not an A, right? This is going to go right into my percent yield calculation. And the other thing that's important is if I have an actual yield of ipentyl acetate, then really what I need to calculate first is the theoretical yield of ipentyl acetate. So that product is going to be my B, the substance where I'm going to try to figure out, okay, theoretically, what was I supposed to make? Starting with two reactants, right? I've got quantities of both the acetic acid and the ipentanol. I'm going to have a limiting reactant problem. So like I did in the last example, starting with my A1, I've got 25 grams of acetic acid. Molar mass was given. It's 60.06 grams. The mole ratio is 1 to 1, so 1 mole of acetic acid, I'll just abbreviate AA, goes to 1 mole of ipentyl acetate, IPA, that might mean something different. All right, and then 130.21 grams was the molar mass of the ipentyl acetate. So from that 25 grams of acetic acid, I could make 54.2 grams of the ipentyl acetate, the product. Now, that again, that assumes that I have plenty of ipentanol to make that happen, and I don't. So I got to start over. Take my 25 grams of ipentanol, just call it IP. Molar mass, 88.17 grams. Mole ratio is 1 to 1, so 1 mole of IP goes to 1 mole of the IPA, the ipentyl acetate. And then 130.21 is the molar mass of the ipentyl acetate. So from that 25 grams of the ipentanol, I could make that doesn't seem right. Hold on one second. 25 divided by 88.17 times 130.21. That's much better. 36.9 grams of the ipentyl acetate. So my max theoretical yield is the 36.9 grams because it tells me that the ipentanol would have been the limiting reactant. It would have run out first, which means at the end of this reaction, the acetic acid would be present in excess. And so that 36.9 that I just calculated, right, that is in theory. If everything's perfect, that's what I should get. Now, according to the question, my actual yield was 19.2 grams. But based on my calculation, I should have had 36.9 grams. So when I do my percent yield, I take my actual of 19.2, divide by my theoretical of 36.9, times 100. Don't round to a whole number, keep your sig figs. So I get 52.0% for my yield of the ipentyl acetate, right? So much more going on in this question, but just know that whenever you're asked for a percent yield, right, you have to have your actual yield given to you. And sometimes that can be hard when you have 3 numbers thrown at you. So pull out the quantity of the product, because if it's a percent yield, right, yield means product. So you're always going to be using that quantity of product as the actual yield, which means that's what you have to figure out for your theoretical yield. So take your other reactants, convert them to that product to figure out in theory how much could you have made. If it's limiting reactant, whichever one produces the smaller amount, right, that's the max yield you could get, because it tells you that that reactant runs out first. Once you have your theoretical, go back, get your actual from the question, actual over theoretical times 100, and that gives you your percentage. All right, so that's how you do limiting reactant questions. All right, we got another one here. On the next page, it says, if 5 moles of NO2 and 1 mole of H2O combine and react completely, how many moles of the reactant in excess are present after the reaction has been completed? So this is something that comes up. We didn't do it in intro, but it comes up in Chem 1, where now we're looking at how much is excess. So if you imagine when I do this reaction based on the balanced equation, I need 3 moles of NO2 and 1 mole of water to react together. If I have 1 mole of water, but I have 5 moles of NO2, I'm only going to use 3 of those to react with 1 mole of water. So that means 2 moles is going to be excess. All right. So instead of using moles, so let me just write that, it would be 2 moles of excess NO2. But instead, let's change this to mass. Okay, let's say I've got 25 grams of NO2 and 25 grams of water. And now I look at what mass of excess reactant is left. All right, so instead of doing moles, let's make it just slightly more complicated and look at mass. All right, so if I have 25.0 grams of NO2, 1 mole of NO2, molar mass 14.01 for the nitrogen, 32 for the 2 oxygens, 46.01 gram total. And this will tell me how many moles of NO2, but what I'm going to do is go ahead and compare it to the H2O. So for every 3 moles of NO2, I need 1 mole of H2O. Then 1 mole of H2O is 18.02 grams. So when I do this calculation, 25 divided by 46.01 divided by 3 times 18.02, to have 25 grams of NO2, I would need 3.26 grams of water. Let me just type it in one more time, just make sure I didn't type anything in incorrectly. All right, so 3.26 grams of water would be needed to react with the 25 grams of NO2. So that means that if I put the 25 grams of NO2 into the container, it would combine with 3.26 grams of the water. But I had 25 grams of water. So 25 grams of water minus the 3.26 grams that I used. I'll follow my decimal places here. I'm only going to go one place past the decimal. So 21.7 grams of water would be present in excess. So a little bit different than what we did in intro, where we just kind of went for how much product we could make. This is another way you can do these calculations, was look at what's left over. What didn't you use? So we took the first reactant, figured how much of the second reactant we would use, but based on the fact that we had much more present, right, the difference, we started with 25, we only used 3.26 to combine with the NO2. That means 21.7 grams of water would be left over. All right, that's a good place for me to stop because the next video is going to do equation writing.